start.
Hello, my dear students. I want to quickly finish Chapter 3. I'm going to talk fast and try and get through this as quickly as I can. It's simply about naming compounds, but it's really more than that. It's how do chemicals come together to form these different compounds. Remember, a molecule is two or more atoms. A compound is two or more different atoms. And so we can have a molecule of hydrogen, N3, but when we mix nitrogen with oxygen, for example, in this compound here, which, is really nitric oxide, is its trivial name. We'll give you its real name in a minute. We've made a compound because it's two different atoms. So I'm covering section 3.12, the last sections in chapter 3, and if you would like to follow along in a different window or pull this up, in our PowerPoints, it starts at about slide 99. And some of the visuals there are quite good. Obviously, it's not something I can replicate here in my kitchen in Grady, Arkansas. So, quickly, we're going to talk about naming compounds. Some of you have had high school chemistry, some of you have even had AP chemistry, and this is old hat to you. A lot of people, this just comes intuitively because they've been hearing about these chemicals, these compounds, and there are other classes in biology and nursing classes. You hear about chemicals from a standpoint of body systems, salts in blood, drugs are chemicals. So there are lots of reasons people sometimes, not sometimes, I think a lot of the times just kind of get this intuitively. And when we start formalizing it, I don't want you to think it's particularly difficult. We're going to start simply with naming binary compounds. Compounds with two different species in them. Binary ionic compounds, which for the most part are salts, a mixture of a metal plus a nonmetal. Sodium chloride, a salt. Okay? And we're also going to talk about binary organic are in there, but binary covalent compounds. So we have ionic and covalent compounds. We're going to name the binary ones first and make them the simplest, but we're going to build up to more complex molecules as we go along here. So when we name a binary ionic compound, for example, sodium chloride or table salt, we have two components, a metal plus a nonmetal, a positively charged cation and a negatively charged anion. We name the cation first and the anion second. Sodium chloride, positively charged sodium with a +1 charge. It's group 1. It has 1 electron. It loses that electron. You lose the negative electron. You get more positive. All of a sudden, you're +1. And remember the rules. If you are group 1 or group 2, and really group 3, if you, at least for aluminum, and I want to say gallium, if you want to know the charge, there are several ways to tell, but the charge is equal to the group number when those metals ionize, lose electrons. Metals lose electrons and become more positive. The nonmetals tend to gain electrons and become more negative, and those will have, in general, at least for the group A's, where we have the most consistency, and for purposes at least of testing, those will have a charge equal to the group number -8. Okay, so chlorine is group 7. 7 minus 8, it's going to have a charge of -1. Sodium +1, chlorine -1, come together to form sodium chloride. You start with a soft, explosive, highly reactive metal, a toxic poisonous gas, mix them together, and you make something we eat on our French fries, in the pounds every year. So, we really want to talk about these compounds and name them. But why don't I say sodium chlorine? Well, the rule is, when you have a binary ionic compound, the anion, you drop the ending and you change it to ide, I-D-E. So we'll have not chlorine, bromine, fluorine, iodine, and astatine, but we'll have bromide, chloride, fluoride. I forgot who I've listed. Iodide. I don't have a periodic table on the wall like I need to be effective. But not just the group 7s, okay? Not just the halogens. Oxide, sulfide, phosphide. Hydrogen can have 2 different valences, +1 or -1. And if we have hydrogen -1, it would be a hydride, okay? So we add ide to the anion and we name it that way. But there becomes a problem when we start talking about the group B transition metals. And also 2 other metals in the group A, lead and tin. Those are actually group 6. Group 6? 1, 2, 3, 4. Those are group 4. Again, I don't have my periodic table with me. And they can have multiple valences. They can, lead, for example, can be +2 or +4. Tin can be +2 or +4 too. I don't have my periodic table and my charts with me. But we know many of the other metals, like iron can be +2 or +3. Copper can be +1 or +2. And we have to know which form of those metals we're talking about. And they have a very simple system in the modern system of naming them. If I mean copper +2, I call it copper 2. So if I make a compound with chloride, it would be copper 2 chloride, or CuCl2. But how do I designate that 2 when I'm writing out the name? I designate it with a Roman numeral in parentheses. And I'm going to show you some examples of this. I'm going through all the rules and then I'm going to go back and work some of the examples that are given in your PowerPoints. And remember, I love giving you test questions that are representative of what you've seen already, so that you don't have to wonder about what to expect. So we're going to add a Roman numeral. In the old days, we would say, instead of iron 2 and iron 3, we would call them ferric and ferrous ions. The ferric was +3, the ferrous was +2, but you can't always do that. For example, with copper, using its Latin name, we would call it cupric +2 and cuprous +1. The ick, you couldn't say what absolutely its valence was, what its charge was. All you knew was that the ick was 1 charge greater than the us. And so we had ferrous and ferric, cuprous and cupric, plumbus and plumbic. Those names confuse people. Plumbus and plumbic. Plus plumbus, +2, plumbic, +4, respectively. And so the new system is much better. You look at a Roman numeral, you know what the Roman numeral equals? It equals the charge on the metal. End of discussion. So, and I'll show you some examples of that. Now, it does get more complex. We're going to have some ions that are not elements, okay? They're called polyatomic ions. There are a number of them. Most of them are oxyanions. Polyatomic oxyanions containing oxygen. Not all of them. Okay, some polyatomic ions like ammonium are positively charged and don't have oxygen in them. It's NH4+. The cyanide ion, Cn-, for example, is another one. So they don't all have oxygen, but the majority and the most important ones that I want you to know will, and I'm going to give you some names and examples of those. we have some rules for naming them. When these oxyanions, and the examples you've heard of them, carbonate, phosphate, sulfate, chromate, chlorate. When you see that 8 on the ending, that is indicative of an oxyanion. And, for example, sulfate, SO4, exists with a -2 charge, but it exists in another form, SO3, also with a -2 charge. Also with a -2 charge. And we call that sulfite. And so you'll have sulfite, nitrite, phosphite. And all those are the same as the 8 form, except one less oxygen. So before we get to the covalent compounds, let's practice naming and learn by example some of the ionic compounds and name them. So I couldn't remember. I think I'm starting out wrong. I think it starts with cesium chloride, but I couldn't read my writing. So cesium plus oxygen would be cesium, there's an A in there if you're from England, cesium oxide. I took the anion, O2 minus, and I changed oxygen to oxide. The next one is cesium, I think, so I won't make mistakes. I'll put my glasses on, even though I'm writing big. Cesium chloride. Aluminum is my metal, my cation. It's going to form a +3 cation. It always forms a +3. It's a group 3A metal. This is aluminum chloride. Chlorine is my anion. I drop the ene and add ide. Okay? So it becomes aluminum chloride. The same way when we mix sodium and chlorine together, we get sodium chloride. This one, in this case, hydrogen, is present in a form as the negative anion. And so this is lithium hydride. This next one, calcium chloride, a drying agent. Calcium chloride, at least in its anhydrous form, chloride is there. And there's one thing I want to point out about this. I'm going to give you these and ask you to name them. Good news is it'll be multiple choice, and it'll also be open book, and you'll have as much time as you need. But, these are done one way, but what happens when I give you the name and ask you to give me the formula? So, like I said, there'll be multiple choice. You'll have a number of options here, and you'll have to pick the right one. Potassium iodide is Ki. Okay? We're going to see this in Lab 12. And this potassium iodide, K is group 1 metal. I is a group 7 halogen. This has a +1 charge, this has a -1 charge. Remember, when I put these together to form a compound, even though the ions are charged, they must come together to form a neutral species, a neutral compound. Calcium oxide. Calcium is +2. Oxygen's a group 6. It has a charge of -2. So a +2 and -2 come together to form calcium oxide. Galenium bromide. Galenium is a +3, group 3 metal under aluminum. And it comes together with bromine, which has a -1 charge, like all the halogens do. So I'm going to need, because this is +3, this is -1, I'm going to need 3 of these to neutralize that. So here's the trick. When I put these together, if I gave you cesium chloride, your choices might be CsCl, CS2Cl2, CS2Cl. But I know that cesium's a group 2. It has a charge of +2. Chlorine is minus 1, so I'm going to need 2 minus 1s to balance out my plus 2 on the calcium. So that's how you tell how many of each go together. Smallest whole number ratio that gives you charges that balance. The biggest challenge is always things like aluminum oxide. That's as hard as it gets. Aluminum with its plus 3 and oxygen with its minus 2. Uh-oh, what do I do? Aluminum's plus 3, oxygen's minus 2. 2 and 3 don't fit together real well. What do? I find what's basically the lowest common denominator, which is 6. So I need 2 plus 3s and 3 minus 2s to form this compound, aluminum oxide. Now notice I did not put the numbers in there. I didn't say dialuminum trioxide. I don't have to with these ionic compounds because there's only one way they can go together to form a neutral compound. So because I know, if not my charges on these, I know how to look on the periodic table and extract my charges, and I know they only go together one way, I don't have to specify numbers. So this compound would be calcium chloride. But, here's cobalt. And so cobalt has different forms. In this one, bromine is a group 7 halogen. It always forms a minus 1 ion, bromide ion. But this cobalt can have different charges. When you look on your Flynn periodic table of the elements, and I'm sorry I don't have one at home and I can't get one right now, you will see when you look at those valences in the bottom right corner of the front side of the chart, the different valences that a metal or a substance can have, the most common one in bold type. And cobalt can have several valences. One of them is 2, so this is called cobalt. I have to specify the form with a Roman numeral 2 chloride. And of course we have to go the other way. Magnesium can have different forms. Not writing consistently. Magnesium can have different forms. One form is obviously plus 4. Oxide can't. At least not right now with us, okay? We're going to assume it always has a minus 2 charge. And it is magnesium plus 4. Oxygen's minus 2. MgO, I'm going to need 2 of those. So when I give you its name and ask you for its formula, you go the other way. You're going to be practicing this in the Lab 12 down below this lecture posting. And by the way, this is the last post for Chapter 3. I hope to get the test up any day now. I won't say tomorrow. I'm still typing and formatting, but I will say soon. Certainly by the weekend, and I'll leave it open really as long as we need, but let's take a week. And here's lead 2 chloride. So there are 2 different forms of lead, plumbous and plumbic. This one would be the plumbous chloride. It also can be plus 4, but this lead, Pb, has a plus 2 charge because the Roman numeral says it does. Chloride's always minus 1 is group 7, so I'm going to need 2 of those. PbCl2. Okay? So, let's practice naming some polyatomic ions. And here are some common ones, okay? So here is sodium sulfate, because SO4 is sulfate. Now, if we were in class, I would point over to my table of the polyatomic ions, and I would also have handed out a copy of it to you. Maybe I'll post the handout that I usually give. But, you know, you're going to have your book and all your notes with you. But sulfate is a very common ion. We've used ammonium sulfate in our Lab 4. And so there are all kinds of salts can form with sulfate. In this case, this is sodium sulfate. I'm going to have to draw it right smaller to fit it in here. I don't have to put any numbers in here because sulfate is always -2. Sodium is always +1. It's a group 1 metal, 1A metal. And so the only way this can go together is this is always -2, this is always +1. I always need to have 2. So I don't need to specify it. Now this is phosphate. PO4 is phosphate. Has a -3 charge, always does. But this is hydrogen, actually dihydrogen phosphate. I'll have some comments about that later when we talk about sodium bicarbonate, perhaps in the lab. So this would be potassium. I'm going to run out of room here. Dihydrogen. Just look along on your PowerPoint. Dihydrogen phosphate. They've kind of complicated the matter there. Here is iron nitrate. Okay? So this is iron, but remember, iron is a group B metal with multiple valences. There are a couple that don't have multiple valences. I'm trying to remember what they are. One of them is silver, it's always +1. And I want to say the other one is always zinc, which is always +2. But except for those that only have one valence, and you can tell that from your Flynn periodic table, most of the group B metals have multiple valences. This has 3 nitrates. Nitrate is always -1. NO3 minus. There's 3 of them, so this must be iron Roman numeral 3 nitrate. Okay? Here's manganese hydroxide. Be careful. Mn is manganese, not magnesium. So, and again, it can have multiple valences. So this is manganese, Roman numeral 2, because this OH minus, this hydroxide ion, it's a polyatomic ion. It's an oxyanion, but it's named hydroxide, so it doesn't have an H or an ite in it. But it's what constitutes a base. If you produce OH, you're a base. We will be getting to acid-base discussion soon. So, this is manganese 2 hydroxide. Then the last 2 are simple group 1 metals. There's never any doubt. This is sodium sulfite. See? Sulfate was SO4 2 minus. Sulfite is SO3 2 minus. 1 less oxygen. So the 8 becomes ite. Now what if I had SO2? Then I would actually add a prefix called hypo, which means below, as in hypodermic, goes under the skin, or hypoglycemia, where your sugar in your blood, emia means in the blood, goes down, okay? It would be called sodium hyposulfite. What if I had SO5? There's no such thing that I know of, but if I had an extra oxygen, it would be called, we would add the word per, as in hydrogen peroxide has an extra oxygen. And the best set of those are the chlorates. You have chlorate, chlorite, hypochlorite, also known as bleach, and perchlorate. And actually perchloric acid is a fairly commonly used acid in the chemistry lab. So it gets more complicated, but just remember 8 and ite. Ite has 1 less oxygen than the 8. But I can't make any rules about it because, for example, SO4 is sulfate, SO3 is sulfite. 4 versus 3 oxygens. For the nitrate, NO3 is nitrate and nitrite is NO2. So the 8 has 3 and the ite has 2. So all you can say is the ite has 1 less. You can't put any hard numbers on it. And finally, sodium carbonate. 2 sodiums. Carbonate is always 2 minus, and that is sodium carbonate. So, that's it for the binary ionic compounds. Let's talk about binary covalent compounds, where we have things held together by covalent bonds. And your book has, and your PowerPoint has a nice table with a bunch of nitrogen compounds. And I'm just going to go through and name them and show you some rules for naming binary covalent compounds. And so this one you probably know as nitrous oxide, which you go to the dentist and it's used as anesthesia, but its official name, that's actually a trivial name, is dinitrogen monoxide. Okay? And then this one, which we actually call nitric oxide, is nitrogen monoxide. You may have heard of carbon monoxide. This is a very common, I want to say pollutant, but it's also something used in your body as a messenger. For example, you may have heard of people taking nitroglycerin tablets to help their heart, but it's because that releases the nitrogen monoxide, also known as nitric oxide, which in turn causes arteries to relax in the body. The next one is nitrogen dioxide, definitely a environmental pollutant. Nitrogen dioxide. Okay, this is why we have catalytic converters. And it's a brown gas. You see it contaminating solutions of nitric acid, for example. When it breaks down, it turns that nitric acid brown as the gas dissolves in the nitric acid and forms. The next three, this is dinitrogen trioxide. And I want you to notice what I'm doing here. This is dinitrogen tetroxide. And the last one is dinitrogen pentaoxide. These last three are all wonderful oxidizing agents. They help things burn. They've been used in rocket fuel. Some of them are nice, stable, relatively stable solid compounds. So, when we name these, we name them with Greek prefaces or prefixes. Numerical, Greek number prefixes. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. So, everyone's heard of an octagon. You know there's 8. Everybody's heard of the pentagon with 5 sides. Everyone may have heard of a, hexagon. And so, you use those Greek number prefixes. The only time you don't have to use a prefix is if the first atom is a single atom. You don't have to say mononitrogen monoxide. The mono is understood. So, this is ridiculous, but you may have heard this. They play this game in high school chemistry. H2O, which we all know as water, that's its trivial name. Its official name would be dihydrogen monoxide. Except everybody would look at you funny if you actually said that. Its official IUPAC name, according to the naming rules, would be dihydrogen monoxide. However, it's known as water so much, that's the way it's going to go. So let me show you a couple of examples. PCl5, and we'll look at some of these structures when we review some material in Chapter 4. I have some models of these. This is phosphorus. So I don't need to say monophosphorus. Penta, 5 chlorines. Penta, this is a separate word. Penta, I did it too close and I left out the end. Penta chloride. The next one would be phosphorus. Phosphorus trichloride. And finally this last one, which is what? Kind of the smell of a match after you've lit it and you smell it. Also kind of the smell of Pine Bluff. Is sulfur, S-U-L-F-U-R with an F in America, P-H in England, sulfur dioxide, SO2 gas. Okay? And then, in addition to being given a compound, you also need to be able to work problems where given the name, you can work backwards to the formula. Now this isn't entirely fair because this is more an ionic compound, so I don't know why it's was included in the lecture notes. So this is vanadium 5 fluoride. So we know with the Roman numeral there that it has a valence of 5, so I need 5 of the group 7 halogen fluorine. So it would be VF5. Dioxygen difluoride would be 2 oxygens, 2 fluorines. Rubidium peroxide. Rubidium is a group 1 metal. It has a +1 charge, but the oxide and peroxide ions, O-, O2-, and O2 2-, both have a 2- charge, so I need 2 rubidiums to balance that peroxide O2 -2 charge. So, oops, rubidium 2, oxygen 2. This is an unusual anion, polyatomic anion, the peroxide. But it would be just like H2O2 and hydrogen peroxide. Rubidium is another group 1 metal just further down in the periodic table. And then gallium oxide. Gallium, I don't have my periodic table with me, but it's a +3 charge. Oxygen's always a -2, so I have the same problem with aluminum oxide. I need gallium. I need 2 of those and 3 oxygens. And just follow the rules. Your book has some flow charts if you're a visual flow chart organizing type of person. And I'm going to give you some practice with this in the video lab that I have further down in our Moodle show. Now the last subject, quickly in the last minute, that I want to cover is acids and naming of acids. Acids, we haven't done a lot with acids yet, are compounds that, depending on how you define them, but in the classical Arrhenius acid, they are compounds that give off H+. We're also going to have Bronsted-Lowry acids and Lewis acids. One Lewis acids are define the acids by how the electrons move about, and the Bronsted-Lowry make them not just hydrogen donors, but also OH acceptors, things that lower pH. But for us, right now, an acid is something that produces hydrogen ions, H plus ions, also known as protons. Okay? And if you're talking about a simple binary acid, you add hydro to the name and change the "ide" to "ic." So, for example, if I have the compound hydrogen fluoride, it's a highly polar covalent compound, but as soon as I put it into water, those dipoles in the water give me some dipole-dipole interaction, and this actually is so polar covalent that this is an acid. The H and the F can come apart to give me H plus and F minus. It's hydrofluoric acid when I dissolve this hydrogen fluoride gas in water. So my "ide," hydrogen fluoride, my "ide" became "ic." And I added the hydro. So hydrofluoric acid. This is the one that dissolves glass, penetrates skin, and then ionizes and causes lots of damage. So it's really dangerous to work with. I don't like working with it. And, that is used, like I say, by artists to etch glass. So you have to store it in plastic bottles because it dissolves glass. The next one's very common. It's sold commercially under a trivial name of muriatic acid. People use it to clean pools and concrete. It is hydrochloric acid. Right? If we name this ionic binary compound, we would call it hydrogen chloride. But dissolved in water, it's hydrochloric acid. A good, strong, common laboratory acid. When you see a bottle with a blue cap, that's hydrochloric acid. And these are color-coded, by the way. Hydrogen bromide becomes hydrobromic acid. Now, some of the most commonly used acids, of course, are, in the lab, are made from polyatomic ions. So, for example, nitrate combines with hydrogen to form nitric acid. In fact, the purpose of some of those nitrogen compounds we saw in the previously and we're practicing naming are used industrially to make nitric acid. But this is nitric acid. And the rule is, if I start with the 8 salt, I end up with the ic acid. I've written it in both places in my summary sheet over here too. This was just to remind me what to cover. So you can see we're at the end. And if you start with the ite, if I had HNO2, and I do here, this is nitrite. If I had NaNO2, I would have sodium nitrite. In the lab, the lab protocol called for writing down and naming sodium nitrite. But I couldn't find any in my chemical stockroom, so I substituted sodium nitrate. But this nitrite salt, the ite salts, become the, oops, I wrote this down wrong, become the us acid. So this becomes nitrous acid. Again, nitric acid, by the way, is one of the more common ones for us to use in the lab. Sulfate, SO4, sulfate anion in our list of polyatomic ions. You're going to see it on that list and that table on page 1 of lab 12. Sulfate is always -2. So sulfuric acid has 2 hydrogens, 2 dissociable hydrogens. So this is sulfuric. So the 8 sulfate becomes ic acid, sulfuric acid. And here's the H2SO3, one less oxygen, that's the sulfite ion. It becomes sulfurous acid. And here is phosphoric acid, H3PO4. The phosphate ion, PO4 3-, you know, phosphates are present in nucleic acids, often added one at a time to proteins, usually in control mechanisms, but they're a common component of DNA because the phosphate has, you know, 3 valences, so it has 2 that it can use on one side or the other of the phosphate molecule to link 2 nucleotides together and form the phosphodiester bond that forms the backbone of the DNA. So phosphoric acid, the phosphate becomes the ic acid again. And then there's one other one listed in your book that's very common, and that is, it's called C2H3O2. What the heck are they doing with that? And this is the acetate anion. If you look on your charts, it's drawn that way for a reason. I'm going to use a different color. Because this group, this acetate anion, stays together. As a biochemist, I always draw it that way. Its structure is this. This is how everything's hooked together. And you can see I can get an H+, form an ionic bond in this acid between this part. And so you're going to see crystals of sodium acetate. I'm going to put an Na+ here with this acetate minus anion. You know it as acetic acid. That's what we're going to call it. Its formal name is ethanoic acid. And it is also trivially known as what? Vinegar. Okay? So, this H can come off here or here. People draw it different ways. It's frequently confusing. And it's also frequently abbreviated. So, biochemists are real bad about this. We'll just write it as HAC and let you, there's no such element as AC, and let you know that that AC corresponds to this acetate anion. But this is acetic acid, a weak acid that doesn't ionize completely in water, which we'll get to when we get to our kinetics. So that's all. I want to close this out. I know it's a long, relatively long video, but this and one more little lecture I have about Vesper are all you're going to need to take the next test. So until the next video, stay safe, quarantine in as much peace and as much safety as you can, and don't forget to study chemistry once in a while. See you in the next video.